Hello, classmates. Diodes are commonly used components in electronic circuits. Taking advantage of the unidirectional conductivity of diodes and the small forward voltage drop when conducting, we can perform rectification, detection, clamping, limiting, switching, as well as component protection and other tasks. In this lecture, we will learn about diode application circuits. The teaching objectives of this section are: first, to be able to analyze diode application circuits. Second, to be able to build a single-phase rectifier circuit and conduct tests. Rectification. The so-called rectification is to convert alternating current into pulsating direct current. Many electronic products in our lives require direct current for power supply. Diodes are applied in rectifier circuits by utilizing their unidirectional conductivity to form a rectifier circuit. Then, after filtering and voltage stabilization, we can obtain stable direct current. Clamping. In the figure, if the potential at point A is 0, then the diode conducts. Due to its small voltage drop, the potential at point F is also clamped around the potential at point A. That is, UF approximately equal to 0. Limiting. In this circuit, let the input voltage be UI equals to 10 sin phi Tesla volt. US1 equals US2 equals 5 volt. And the diode is ideal. When UI is the positive half cycle, VD2 is cut off. When UI less than or equals to 5 volt, VD1 is cut off. The output voltage changes with the input voltage. When UI greater than 5 volt, VD1 conducts. The output voltage equals US1 equals to 5 volt. Similarly, for the negative half cycle, thus we obtain graph B. The output voltage is limited between plus or minus 5 volt. Half of the amplitude of the input voltage is cut off. The amplitude of the output voltage is limited. Component protection. In electronic circuits, diodes are often used to protect other components from damage due to excessive voltage. In this figure, when switch S is closed, power supply E supplies power to the coil. Current flows through L, storing magnetic energy. When switch S is suddenly opened, an induced electromotive force EMF EL will be generated in L. The EMF EL and the power supply E superimpose on the switch terminals. This can cause spark discharge at the terminals, affecting the normal operation of the equipment. The role of this diode is to discharge through EL in the diode when the switch is opened, keeping the voltage across the switch terminals from becoming too high, thus protecting switch S. At this time, the diode is also known as a freewheeling diode. Now, let's focus on single-phase rectifier circuits. Single-phase rectifier circuits include half-wave rectification, full-wave rectification, bridge rectification, and doubler rectification circuits. When analyzing rectifier circuits, for simplicity, diodes are treated as ideal. That is, the forward conduction resistance is 0. and the reverse cutoff resistance is infinite. This diagram is the circuit diagram of a single-phase half-wave rectifier. Transformer TR transforms the sinusoidal alternating current U1 from the power grid into U2. Let U2 equal to square root of 2 U2 sine phi t volt. During the positive half cycle of a cycle, U2 has a positive polarity at the top and negative at the bottom. The diode can conduct. The output voltage across the load equals U2. The waveform changes following the variation of U2. During the negative half cycle of U2, the polarity of the voltage is negative on top and positive at the bottom. The diode is reverse biased and cut off. The circuit is not conductive. There is no output voltage on the load. Thus, the voltage across the load is obtained, and the current waveform is seen in the curve diagram on the right. That is, when U2 greater than 0, the diode is forward biased and conducting, ignoring the forward voltage drop of the diode. U0 equals to U2. When U2 less than 0, the diode is cut off. U0 equals to 0. Let's look at this diagram. The alternating current U2 on the secondary side of the transformer becomes a single-phase pulsating direct current voltage on the load. Then, the voltage UD on the diode is exactly opposite to the output voltage. The voltage is 0 when the diode is conducting during the positive half cycle. When the diode is cut off during the negative half cycle, UD equals to U2. The diode only conducts electricity for half of the cycle, and the voltage obtained on the load is in a single direction, with magnitude varying over time. Unidirectional pulsating voltage, the average value of the output volt, we can calculate and obtain U0 equals to 0.54 U2. If the circuit load is known, then the average value of the rectified output current is I0 equals to U0 over RL equals to 0.45 U2 over RL. We wire according to the diagram. Choose U2 as 9 volts. Connect the anode of the diode to the 9 volt on the secondary side of the transformer. Connect the cathode of the diode to one end of the 1 kilo ohm load resistor. Connect the other end of the load resistor to the 0 volt on the secondary side of the transformer. Measure the voltage across RL with a direct current voltmeter. Measure U0 to be approximately 4 volts. It is almost equal to the theoretical value. When selecting the diode, we should pay attention, because the average current on the diode ID equals to I0. So, when selecting the diode, the maximum rectification current IF of the diode should be greater than the load current I/O, the highest reverse voltage value that the diode can withstand.
UDRM equals to square root of 2U2.
The advantages of a single-phase half-wave rectifier circuit are simple structure, fewer components. The disadvantage is that the output direct current component is relatively low, and the ripple of the output voltage is large. The utilization rate of the power transformer is also low, so it can only be used in applications where the output voltage is relatively low and the performance requirements are not high. Single-phase half-wave rectifier circuit only utilize half of the power supply cycle, and the pulsation of the rectified voltage is relatively large. For this reason, a full-wave rectifier circuit is often used. The most common is the single-phase bridge rectifier circuit. The following are several common ways to draw a single-phase bridge rectifier circuit. The working principle of the single-phase bridge rectifier circuit is: when the voltage U2 on the secondary side of the transformer is in the positive half cycle, the polarity of the voltage is positive on top and negative at the bottom. Diodes D1 and D3 conduct. Wire diodes D2 and D4 are cut off. The direction of the current is as shown in the figure. After diodes D1 and D3 conduct, the output voltage equals U2. The waveform changes following the variation of U2. When the secondary voltage U2 is in the negative half cycle, the polarity of the voltage is negative on top and positive at the bottom. Diodes D2 and D4 conduct. Wire diodes D1 and D3 are cut off. The direction of the current on the load RL still flows from top to bottom. The polarity of the output voltage remains positive on top and negative at the bottom. The magnitude is the same as U2, but the polarity is opposite. From the animated demonstration of the waveform diagram, we can instinctively see what is obtained on the load is also a unidirectional pulsating direct current voltage. The difference from half-wave rectification is that on both halves of a cycle, there is an output voltage, so the efficiency of full-wave rectification is higher. The average value of the output voltage should be twice that of half-wave rectification. U0 equals to 0.9 U2. Let's do a verification experiment. First, connect the 4 rectifier diodes. Connect the cathode of D1 to the cathode of D2. Connect the anode of D3 to the anode of D4. Connect the anode of D1 to the cathode of D4. Connect the anode of D2 to the cathode of D3. Set U2 to 9 volt. Connect the anode of D1 to the 9 volt on the secondary side of the transformer. Connect the anode of D2 to 0 volt. Connect the cathode of D1 to one end of the load resistor. Connect the other end of the load resistor to the anode of D3. Measure the output voltage value with a direct current voltmeter. We can see the value is around 8 volts, which is close to the theoretical value of 8.1 volt. The voltage and current of the bridge rectifier circuit, the average value of the output voltage UO equals to 0.9 U2. The output current passing through the load resistor, IO equals to 0.9 U2 per RL. The current passing through each diode is only half of the output current, ID equals to 0.45 U2 per RL. The highest reverse voltage each diode can withstand. UDRM equals to square root of 2 U2. From the above analysis, it is known single-phase bridge rectifier circuit has a large direct current component of the output voltage and a small ripple, and the average current passing through each diode is also small. Therefore, the single-phase bridge rectifier circuit is the most widely used. Well, that's it for this lesson. Goodbye, classmates.